Hello everyone. In the previous video, we were discussing about the simply connected region, and in this video, we're going to discuss the multiply connected region. So, as I had mentioned earlier, uh, basically, when you have this kind of a two-dimensional region and you have holes inside it, represented by uh, these regions, this is referred to as a multiply connected region, as opposed to the fact or to the situation where we would have no holes, which would be simply connected. Okay, so what do we do, or what we have in terms of the Prandtl stress function formulation that is different for this multiply connected region, which is different from the simply connected region? Well, first of all, let us consider the governing equation. That is simply del square psi equal to -1, and this governing equation remains unchanged. Whether it is for the simply connected region or the multiply connected region, it's the same thing. Next, very importantly, we had earlier mentioned uh, that psi is equal to constant on the periphery. This was our general conclusion from the theoretical development. Psi must be a constant. Now, in the simply connected region, what we had said was that since there was only one periphery involved, we took we were free to consider the simplest uh, consideration for that psi uh, on that single periphery, which was that psi is equal to 0. But we no longer have that luxury in the present in the case of this multiply connected region. So what do we do? Well, it is still true that over each of these peripheries individually, okay, so if you consider this periphery, the psi is a constant here. If you consider this periphery, this is a constant here. If you consider this periphery, the psi will be a constant over this entire thing. The psi will be a constant over this entire thing. So that much remains all right. Okay, so this general conclusion that we had arrived from our general theoretical development, that the psi must be a constant on the periphery, that remains true, but uh, but we must also appreciate the fact that these constants that I had just mentioned, they must be of different values. Okay, so it's a constant here, it's a constant here, but these two constants are different. So also this constant would be a different, this constant will be a different value. Okay, so they're all different values. However, to keep things still as simple as possible, what we can still do is that over the entire outer periphery, we can still consider the psi to be 0 there. It really doesn't change anything because uh, suppose you consider a situation like this, that okay, let me name the contours, the different contours that are present here as so let's say that the outer contour is C0, this one is C1, this one is C2, this one is C3, and if we have other contours, so on and so forth. So on C0, suppose we say that psi is equal to 1. Okay, so this is just like a hypothetical example. Then over C1, psi is equal to 3. Over C2, psi is equal to 2.5, and over C3, psi is equal to. Now, instead of this, you think whether it would really make any difference if I change my baseline such that psi is equal to 0 over C naught. Okay, so what I do is that on each of these psi, I just subtract, or from each of this psi, I subtract 1. So this becomes 0, this becomes 2, this becomes 1.5, and this becomes 3. So overall, just by changing the baseline, it really doesn't change anything, because again, I want to emphasize here that because in the expressions for the shear stresses, sigma xz and sigma yz, which ultimately we have to find out in terms of this Prandtl stress function, that connection is through the presence of the derivatives. Similarly, these governing equations, they all it involves involves the derivatives. Okay, so uh, what is usually done is that on the outer periphery, uh, on the outer periphery, psi is taken as 0. So that is one less thing that we have to worry about. Over the other contours, see, this is just a made up hypothetical example, but in a real problem situation, even if we say that on C0, the outer periphery, psi is taken as 0, but we still would not know a priori what the values of these constants would be over the C1, C2 and C3. We really have to actually find those things out. They are unknown. So on the other peripheries, inner contours, psi is a constant on each of them, but the constant values themselves are not known. So we have to solve for them. All right. Now, depending on the problem at hand, we can approach this situation in different ways. And as we go on to do problems, and because of the slightly more complicated geometries that we'll be considering, for example, uh, well, even if you consider the simplest of example, which is the circular annulus, it does involve a little bit of integration. So we were not doing this by hand because that would be just unnecessarily time consuming. We'll just go over to, I'll just illustrate them by some on using symbolic Python. You can also, the people who are not enrolled in this course can directly take a look uh, at the GitHub repository, the link for which I will provide in the description below. But even before we go into such examples, there is a couple of points which is extremely important to note. So remember the all important torsional rigidity. So in the case, so let me just write down the expression here, the general expression. It is minus twice g integration x n x plus y n y. Sorry about that. Y n y times psi over the periphery plus 4g integration over the entire domain, that is an integration with respect to the area. All right, now when we were considering the simply connected region, because we had the liberty of choosing this psi to be equal to 0 over the single periphery available, this entire first term reduced to 0. But now we don't have that luxury. So it will be better if we subdivide this integration in this form. So we say minus twice g integration over the contour C0, this entire thing, ds plus C1, this entire thing, ds plus ds, and so on and so forth. Okay, because I'm writing this as dot 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 because in general it can have more than these three inner contours also. The last one, that remains unchanged. Now if we just consider this first integration over the C0 contour, which is the outer one, over this you see we have this expression x n x plus y n y times c. This c we have already considered to be 0, specifically over the C naught. So this integration is equal to 0. So as I had mentioned earlier, one less thing to worry about. But these other ones, the only thing that we can, the only simplification that we can do over here is to take this psi outside this integration, because that psi would be a constant value over each of these contours C1, C2, C3, etc. That's the only luxury that we can afford. So what we will end up with is this thing: summation I is equal to 1 up to as many inner, so I'll put this as uh, I is equal to 1 to n, uh, where you note that actually what we have is this n, it represents uh, the n inner contours, but in total we do have n plus 1 total number of contours, because the outer one is also a contour. Okay, so actually the index is going from 0 to n. You see this 0 up to n. It just so happens that we have considered the psi to be 0 on C1. That is why the first or the 0th contour, it does not contribute. All right. So the expression is psi I integration over the Cith contour x and x plus y and y ds plus 4g all right. Okay, now this is just one of the points which I had wanted to mention. This is one level of simplification, but we have to be extremely careful about something else also, and that is about the nature of this integration. Well, the point is like this: when we carry out this kind of a cyclic integration over the outer periphery, okay, so this is something which we have to keep in mind, specifically when dealing with multiply connected region. Okay, this is a very special consideration uh, which has to do with the back end mathematics of such integrations. I won't go into too much detail, but in terms of the problem solving, what we need to do is this: that when we are doing the integration over the outer domain, we are actually proceeding in a clockwise fashion. But when we are doing the integrations over this inner contours, we are not going to go uh, this like anti-clockwise, rather we are going to go clockwise. Okay, so I repeat: for the outer periphery of the cross section, we are going to go or we need to go anti-clockwise. For the inner peripheries, for each of these, we have to go clockwise, we have to go clockwise, we have to go clockwise. So let me mark that out by writing like this. Okay, so the arrows depict the uh, the sense in which the integration has to be done. So how does that matter in this particular case? So we'll see. If I just go on to simplify this thing, so let me just write that in the next page. So our Gj is equal to minus twice G, summation I is equal to 1 to n, that is over all the peripheries, the psi I integration over the ith inner contour, which has to be done in a clockwise fashion, x and x plus y and y ds, and the last one is just okay. Now let's take this up separately. Over the Cith contour, we have x and x plus y and y. Yes, let me mention this integration. And when I say integration, I mean this kind of a cyclic line integration uh, over each of the inner peripheries has to be done in a clockwise sense. Simultaneously, also, I reiterate that the integration over the outer periphery has to be done as we have been doing always in the anti-clockwise sense. But right now, I don't need to do that because all that remains is the inner peripheries. Now, you see this x and x plus y and y, uh, if we apply the uh, Green's theorem here uh, in reverse, means that we go to the step, we go back to the step where it involves the derivatives. It should be like this, that del del x of x plus del del y. This is a cyclic integration here. This is not, and this won't be ci also. I'll correct that. So here we have gone from a line integral to an area integral. Correspondingly, this should be changing to ai. Okay, so this result is 1 plus 1 dA. Now you may think that all that you have to do here is to write this as twice ai, and that is fine, except for one little trouble in this entire thing is that this, but when we had said that this integration has to be carried out uh, in a clockwise sense, that clockwise sense that has not been respected. Okay, so because it is a clockwise sense, so this should come out in this kind of a negative sense. Okay, so it's better if we just keep it like this, and then we just say that our result is actually minus twice a because of the clockwise sense. So overall, what does this give us? If we go back here, the torsional rigidity now becomes 4G psi I AI. Okay, so we have this 2 here, we have this 2 here, that gives us a 4. The G is already present, and this AI is here, and this psi I is very much present here. So this is psi I AI. Please note that when we are doing actual problems, you must be extremely careful to note that this summation, it goes over all the uh, peripheries, over all the inner peripheries. Okay, you have to you should not include the outer periphery. Okay, and I mean, even if you did, I mean, there is no problem because the psi would contribute as 0 on the I equal to 0. All right, uh, so this is 4G IT. That's it. Okay, so for the multiply connected region, we have to use this particular expression for the torsional rigidity. Okay, so this is something which we have to be a little bit careful about. All right, so on that note, I will end this video. Thank you very much.